So we have built this game of life in Blender using Python in another video. You can watch it if you like. Now we're trying to improve it based on feedback that I received. I've got some great ideas and I'd like to check them out. Let's go! So in the last video I built this 2.5 dimensional so-called game of life. I put up a video on YouTube and the end result looked a little bit like this. I've also put the code into the description down here, so there it is in a GitHub gist or gist, I don't know how you call it. I'll just copy this code and I'll paste it into a new Blender file. So I switch to scripting, make a new text file and just paste it here. Let's see. Now let's try to make this running. I'll run this and it says System Console grid not found, because this script implements Conway's game of life. It relies on a Blender file containing a mesh called cube, that's this one, and an empty collection called grid. So let's make a new collection that's empty called grid. And the cube has to have a side length of 1. It says here, I think the default cube has a side length of 2, that's right. So I'll size it down to by 0.5. Now it has a side length of 1. Let's run this again, see what it looks like. That's better. I think we can hide the default cube and also hide it for render. I don't know what this means. Alright, so let's get the timeline here. Timeline, and let's select the grid. So that looks kind of nice. That's the last state, and I posted this also on Reddit, and there were a lot of comments, especially one really helpful one from John Wood 2357, and he says an improvement could be to, instead of linear growth, use a logarithmic one, or like a I don't know how to call this in English, negative, let's say it's a yeah, you see 1 minus, so it's kind of like a logarithmic growth. It declines, so the growth slows down the longer the cell is alive. The same with the logarithmic growth. So that's his first suggestion, and John's second suggestion was to try to continue decay after the cell dies. So instead of just being dead, we have to record how long it has been dead. So when it's alive, it jumps back to 0 or 1, I guess, and the longer it's alive, the larger it gets, and the longer it's dead, the smaller it gets. So it grows until under the plane, right? So lower than ground level. And I want to adjust the code to make this, and the first thing I want to do is to implement a sense of age, right? The concept of age, because we don't have that yet. So instead of saying check, so when we are updating it, if it's alive, instead of if self life, we say if self age is greater than 0, I guess. That means it's alive. And it ages, right? So if self age is larger than 0, it probably already is alive. So it is alive, and it is staying alive. So its age increases by 1, and its scale, let's leave that out for now. Let's comment it out for now, and this one too. So if its age is larger than 1, it's larger than 0, it grows older. Else, I guess it grows not really younger, but like more dead. So minus equals 1. So if it's already dead, so if it has age 0 or below, it gets negative age. So that means it's longer dead. And instead of the scale, I want to make it a location, but let's leave that for now. So when we initialize, because we begin with setting up the grid, and then we set up the random life, right? So that's this function, and next life equals true, self update. So instead of saying self.life, when we initialize it, we say self.age equals 0, and then we set it up. We set up the random life. If random, self dot next life equals true. Let's say self dot age equals let's keep next life, and then in the check, let's say if self life, let's say if self age greater than 0, and the sum of the neighbors. That says the same, right? We have the same. But here we have to say if that's life, if the neighbor's age is greater than 0. So we check if the neighbor's age is greater than 0, and if the sum of the neighbors that have an age greater than 0 is between 2 and 3, next life equals true, else next life equals false. So yeah, then if next life, that's if it's if it stays alive. No, if it's alive in the next iteration. If it already was alive, so if self age already was greater than 0, then it's staying alive. Else, it's birth, right? But then there's the other case, that it's dead. This one is it's dead, and then we can say if it already has been dead, so its age minus equals 1. So that's bullshit right here, because it has to say this is the birth, it is alive, but it's staying alive, then it gets older, it is dead, it's dead, but it's born, then the age goes to 1. Now there's another case if it's alive but dies. So we have here, we have to say the case if self.age is greater than 0, it's alive but dies, then self.age equals 0. Else it stays dead, then it has a negative, then its negative life shrinks to become even more negative. So that's that. Now let's check it out. Probably some issues. No issues yet, but we don't see anything because I have commented out the scale factors. So let's put them back in, right? Self-object scale, self-object scale, self-object scale. Let's just see what this looks like. So it looks like this, unsurprisingly, similar as before. So instead of the instead of looking at these things, we now have to look at the age and implement the growth we don't have self.life anymore, so we can delete this. And instead of looking at the scale, I want to set the location. So now we have to say if it stays alive, let's set self.object.location C to, and then I'll just copy John Wood's formula here, log of self.age plus 1 probably, and then we have to scale it with the global size, tile size, yeah, times tile size, right? So we set the location to the log, and for now let's just say if it's dead, then it's 0, and this just adds a keyframe to the location path. Right, so I run this, and now it says chuck, log is not defined, so we have to probably from math import log. Let's see. That looks nice. So as you can see, it stagnates at the end. So as it grows older, it doesn't grow, it doesn't change its C position linearly, but it grows to a point and then gets slower and slower until it like hovers, and if it doesn't die, it should stay there, right? Then the next thing I want to do is I'll take this one, I go to edit mode, and I change the scale in the C direction so there's an overlap, and then it looks like there are growing columns. So that's the linear growth implemented. Now let's check the same. Let's make the second. Let's implement the second suggestion. If you're keeping track of cell height and age separately, then you could have height continue decaying even after cell dies. This should give the animated So, and should go into the plane. So right now, in this last bit of the animation, we have the alive cells, and we have the cells that are reborn and dying rapidly. These are the ones close to the ground. And then we have the dead cells. These are staying at 0. So what we can do is say, for the negative aged ones, we copy this formula, set the location to the negative log of the absolute of the age plus 1. And why the absolute? Because that's the difference between the log of x and log x plus 1. So log x plus 1 has a dead cell has a height of 0, but a cell with age 1 has a height of about 1.3, and a negative aged, so a cell with age minus 1 already has a cell of negative, has its location of negative infinity, so it plummets rapidly. So what we want to do is we want to mirror this curve to the negative x, right? So we take the absolute, then we get this curve, and then we take the negative of it. So this should be the negative logarithm of the absolute. Right, so let's see what this looks like. So, okay, this is interesting. Now they look like they're falling, but when they're born, they shoot up rapidly to make to go up to, I guess, 0, right? No, it's so here we have the 3 states. We have the alive cells, we have the dead cells, and we have the cells that are just born or cells that are just died in the middle. And all the others are in between, that are older and younger. Now, older and alive or longer dead. So this one is just dead, this one is just born, this one is alive for a longer time, this one is dead for a longer time. So these are the differences. And as these lines down here is just the underside of the columns, right? So we have this kind of cool pattern. I want to set the iterations to something like 300, so we have a longer time to look at. And then the other thing I want to try is to set the log, I think that's base E. Let's try base 10 and base 10. Let's see if there's a difference. So that's a bit, it seems a bit smaller, like the movement seems a bit more, seems a bit, yeah. But I think the speed and everything looks kind of the same. Let's try base 2 or base, yeah. So this is base 2. It looks okay. Another thing to try would be to leave it at the, I think the default is log E, of course, and then we could try to multiply the age by, I don't know, 10. Oops. H times 10 plus 1, and then probably divided by 10 times 10 plus 1 divided by 10. Let's see what this looks like. So very small. Divided by 3. So I'd say it looks almost the same. Let's make a little, try 1000 and 300. Really small. So let's try 3000 divided by 30. So that looks almost linear. So let's try the other way around. I'm very bad at intuitive math. 0.01 divided by, multiplied by 30. This should probably be 001 manuscript. So that's interesting. That's kind of strange. Let's try 01. Oh, times 30 times 3 times 3. So that's strange as well, right? Ooh, never stops. No. Let's get back to the default. Oops. So that's the default. Then let's try John's other formula. This one is hyperbolic. I think is it hyperbolic? Probably hyperbolic. Yes. Hyperbolic function. Comment this out. and this would be self.age times tile size, copy, go down to this one, comment this out, and this is times negative tile size and the absolute. Right, run script. So, I think it did something wrong there. Of course, this has to be in parentheses. Run script. So this looks kinda the same. It's almost the same, a bit shorter, but if you stretch it up, times tile size times 2, I don't know, by 2 times 2, it will look almost the same as the logarithmic one. Right. It looks similar. I think it's a cool effect. And now there's the, and maybe this can be a bit, maybe the dead ones should look the same, like the newly died ones could look the same as the newly born ones. So how would we manage this? I don't care. I leave it with this. Thank you for your suggestions, John Wood. I hope I did understand your comment correctly, and I'll make a render and see what the final result will look like. Thank you. If you have any questions, post them below, and I hope everything was understandable, and have a nice day. I just have to add, this of course needs parentheses 2. That's something I did oversee. And what does this look like? Yeah, better. It looks right, and of course, as I said, not that different to the logarithmic growth, but I will post the link of John Wood's comment here, inspired by this comment, and also the original code link is this one. And then I will post the link to the new code in the description as well. Thank you. Goodbye.